The only game really worth playing is creating AGI, or artificial general intelligence. And now we're seeing sufficient motivation to move in that direction because it's clear that the classic LLM plus RLHF, reinforcement learning with human feedback, plus agentic stack is not going to yield that. The field is open to figure out what will. And in this conversation that we're going to be having, we're going to figure out the core. I'm not saying we're building an AGI. That's a little bit more advanced than what we can do. But we're going to be working on the essential core, the beating heart, the central part of AGI, which actually is already fairly well defined. It's well within the realm of a method called active inference. And active inference itself is not quite enough. It's an important component. It's not enough. We'll discuss later how it fits in. But the notions do comprise the essential capabilities that we need for AGI. So with that note, let's begin. I'm Dr. Alianna Maren. I'm the founder and chief scientist with Themyscus Incorporated. I'm the founder of the Themyscus Academy. I've been really, truly spending all my life devoted towards creating AGI back from when I was a teenager and selecting coursework that would move me in that direction. It's only now, of course, that we're having the capabilities to really start honing in on that. Now, active inference. There's a central core equation, which is common also to variational inference. And this equation is the Kullback-Leibler divergence, KL divergence. And it's essentially a way of assessing, is the model close enough to our data? So we are doing a reverse KL divergence where we compare the model against the data, the Q versus the P. The interesting thing here is that we're not just using a regular probability of observed. All of this comparison is being done in the latent space. That is to say, we're doing all of the comparisons on the variables that we can't see. They are based on the observations and then also the model Q of the latent variables. I'm going to show an example here from when I teach AI and deep learning at Northwestern. And in week 2, we run the XOR problem, which is as basic and simple as you can get. It's an XOR, exclusive OR neural network. And the idea is that the trained result is for a non-linear classification. So if you put a 0 and a 0 into the two input nodes of this neural network, the output would be a 0. If you put in a 0 and a 1, or a 1 and a 0, the output should be a 1. But if you put in a 1 and a 1, the output should be a 0 again. That's the nonlinear classification part. Nonlinear separation of classes. In this particular case, showing you a neural network where there are two nodes in the input layer, and in this example there's one node in the output layer. You could have one or two depending on the network design, and then two nodes, which is the minimal necessary number of nodes in the hidden layer. Both the input and the output are observed variables, and the two in the middle, the hidden nodes, are the latent variables. So we've got two kinds of variables here. One is the kind of variable that we can observe, that we can measure directly. And the other kind, the hidden variables or the latent variables, are constructed by the intelligence system. They are based on the observed variables, but these latent variables represent combinations or patterns of the observed variables. We simply can never access them directly. So I'm using this example because it's very visual. We can get it right away. In the Kullback-Leibler situation that we're describing, which can be applied to neural networks, and you'll see references to the Kullback-Leibler divergence in Hinton's early works on the Boltzmann machine, you'll notice that this is the simplest possible example. As we move more into active inference, it's not so easy to find the hidden or latent variables. The important thing is that the intelligence system constructs its representation of reality based on the observed, and it constructs this representation using its own internally created set of hidden or latent variables. And then it creates a model of the values of those latent variables, again, depending on the actual observations. So the intelligence system uses the model to depict its understanding of the external reality based on not the observed variables, but the latent variables that the intelligence system has constructed. What we're going to do together, you and I, over the next several minutes, is take a look at a single equation, the KL divergence, and not do the heavy-duty math. We're not trying to work through derivations or anything. We're going to more or less go into a contemplative state around a single aspect of the breakdown of the KL divergence and consider it at three different levels. And as you gain that contemplative sense and sort of become one with the equation, so to speak, you're going to get layers of insight that will prime you for working with AGIs. So let's begin. The first level, basic KL divergence. Today's discussion focuses on the hidden variable nature of what we're doing, but the next day's discussion in the top 10 terms in statistical mechanics and generative AI course, today being day 16, latent variables, the next day 17 being the KL divergence. We would do the math a little bit more, but right now using the KL divergence to introduce what is going to unfold, we're going to contemplate the entropy term. And the reason that we're doing this is that we want to see for ourselves what's involved in this KL divergence. And the first thing that we'll notice is that it has both aspects that I've described earlier as being fundamental to generative AI. That is, it has the Bayesian component, the probability of one thing depending on another, conditional probabilities, and it's got the stat mech component. By the time that we've converted the KL divergence, again, we would do that in a different discussion, but by the time that we've done that and we've converted it into two components, one involving conditional probabilities and the other involving just the latent variables, we see that that latent variable term looks a lot like a statistical mechanics entropy term. And being that it's an entropy term, that's where we make that connection to stat mech. That's where we make the connection, the crossover to a free energy principle. But right now, we're just going to say, first level of insight, we're combining the two kinds of thinking in one equation, and that's the probabilistic from the Bayesian perspective and the probabilistic from a stat mech perspective. Two worlds, two-dimensional realities, so to speak, brought together into one equation. Second layer, we're looking at that entropy term. It's an entropy term that is written of the model, not the actual latent variables itself, coming from the observed, but the model of the latent variables. And so it's operating in the latent space. And this is a step back moment. It's like, oh, we really can't compute this because we don't know the distribution of the latent space variables. If we did know that distribution, they'd be observable. And then they would be in the observable variable category, not the hidden latent space category, right? So this is a term that makes beautiful sense mathematically. It's just we can't compute it. And as David Bly, one of the very famous researchers working in this area, once said, and I'm paraphrasing him here, I'll find the exact quote and stick it at least into the discussion box. He said, variational inference is what you do while you're waiting for your full computation, that's the paraphrase, to converge. In other words, we really can't compute that entropy of the model in the latent space because we don't have access to that. This is a step back and pause moment. It's like, oh, this is why we have this movement from this basic equation here into the next stage. This is why we have variational inference, which is an approximate method. It's an approximation. Variational inference draws on two distinct intellectual lineages. The variational principle itself has its roots in physics. Richard Feynman devised and applied it to statistical mechanics and path integrals, showing that intractable quantities can be approximated by minimizing a tractable bound. This mathematical machinery was later brought into machine learning by Michael Jordan and colleagues in their landmark 1999 paper, which gives us the framework we now call variational inference. So, variational inference, it comes about because we know that the actual formulation lives as a entropy of the model in the latent space, but we can't compute it, therefore we're doing something else. We're making an approximation. Third, just because we can't compute that entropy directly doesn't mean that we just got to like, oh, well, don't know a thing about it. No, 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 no. We can infer something, and that gives us insight as to what's going to go on inside the very core of an AGI. Because the AGI is going to operate within the latent space, not the observable space. Just like you and I, any living system, any intelligent system that we devise, it's going to take observations of its surround and create a representation of its reality based on those observations, and then it's going to create a model of the representation where the model does the smoothing out. And the model, which is going to have that entropy term, the entropy of the model distribution, it's going to be a classic entropy term. Even if we don't have the details, we know something about entropy. So, one moment here, prop time. Entropy. I'm going to ask you to envision this as a 2D curve. That is to say, this two-dimensional upside down U that you're seeing here with this pole, that's the general shape of an entropy curve. The thing to note is that there's a maximum. Okay, what we're doing with the AGI or the active inference or any intelligence system, what we're doing is we are minimizing the KL divergence. That is to say, we're bringing the model as close as we can to the representation of the observations. And as we do that, as we minimize the divergence, what we're going to do in part will be to maximize the entropy. Now, the entropy is always going to be a downward-shaped bowl, so to speak. And it could get fancy and complicated, but the important thing is that there's a maximum right there. And that maximum, actually, we found it in week 2 of the top 10 terms course. That's why we had the whole top 10 terms course, a gentle lead-in to the whole notions of thermodynamics, including free energy, entropy, enthalpy. And then in week 2, we really formalized some of those notions. We went into microstates and macrostates and the partition function and how do you actually write down the entropy term and relate it back to microstates and macrostates. And what we did with that was we confirmed that the entropy term is going to have a maximum at the point at which you have the greatest possibility of distribution amongst states that all have the same energy. That would be the macrostate collection of microstates. Now, in the KL divergence term, you don't have the entropy like this. You have the negative of the entropy. It's always a bowl facing up, and you're always going to try to reach the minimum of the negative entropy, and it's always going to be modified by an additive term that can shift that minimum for the whole equation to the left or the right somehow. But here's the thing. We know that one of the big terms in this KL divergence in the latent space is still the negative entropy, meaning that there will be a minimum to it. And then we're just going to adjust the minimum of the whole term, the additive plus that, some direction or other. Depends on how the other term nudges it. But here's the important thing. There is a minimum. There is a minimum. What it tells us is that as this intelligence system seeks to bring its model for its reality into alignment with its observed, its representation of reality, it's going to seek to go to a minimum, and that says to us, seeking a stable state. And this is another way of phrasing something that I introduced, it's half a year ago in a different YouTube, saying that AGIs will always seek a stable state. But here we're looking at it a different way. We're looking at it in the context of a specific term and a specific equation, noting that this is operating within the latent space and saying to ourselves, oh, yes, as this intelligence system seeks to refine its model, it's going to be going to a minimum. It's going to seek that minimum. It's going to stay insofar as it can within a minimum energy state. That is to say, a minimum entropy state, and then the other term will contribute an energetic component. That gives us system stability. That is a wonderful, wonderful thing to have in an intelligent system. Stability is much to be desired and praised and sought after. Let me just take a couple of moments and share with you personally as we close out. It's 5:30 in the morning here, and I've been doing semi-round-the-clock editing, and If you and I had a moment to just sit and have a really great cup of Kona coffee together and look out over the beautiful mountains and reflect on what it is that you would need, that we both need really, to transition into this new environment where we are thinking in terms of active inference, and we're using that as the central core around which we're going to be building AGI, how would we both go about learning? And the first thing that I've got to share with you is it takes more time. This is truly a much more subtle, conceptually nuanced set of concepts that we're working with. And let me give you just an example, because last night I was looking up that David Bly quote that you saw just a few minutes ago for you. And it was on Quora. And somebody there had posted something about how we could indeed, in a particular case, get the probability of the latent variables. And here's the thing. Yes, if you define the latent variables in advance, that's called creating the a priori beliefs. And if we're doing a laboratory course and we're playing with all the matrices, then yes, of course we can. So suppose that we're running an active inference system and we take it a few steps down the road and we get new observations. We can continue to compute the entropy of the model of the latent states that are conditioned on our observations, but that is the probabilistic or approximate distribution, where we use a tractable family of distributions that we use to generate the latents from the observations. But we can't compute the exact true posteriori. That is, we don't know what the real values of those latent variables are. We can't compute the marginal. We can't sum over all the possible hidden states simply because we don't know their extent. So can I be honest with you? This last section, just this last minute, was a really tough section for me to produce. And I had to go back and forth with Claude multiple times, multiple iterations, multiple checks on the wording, on whether or not I was getting the concepts right. And often as not, I wasn't. And I had to keep refining and keep refining. And that brings me to my second point, which is use your resources. We are now in a totally different situation than we were even half a year ago. AI assistants, I call them associates for this kind of work, are so much more refined, and they can bring a great deal of knowledge to bear and help you refine your knowledge. It will be a tremendous boost, and I'm sure you've already figured that out. I'm just encouraging you in this practice. And let me mention as an add-in, when I'm talking about using your tools, that does include the new Namjoshi text, Fundamentals of Active Inference, beautifully produced, and we are following his notation, both in the YouTubes that we're producing, like right here, our XY notation. We're using the same notation in the Top 10 Terms course. We're adapting to work with him, and we're also using it along with a notation from the PYMDP code for active inference. We're using that notation in the code base and the documentation for the code as well. So my final suggestion on how to ramp up your abilities in learning active inference is, very simply, you're going to have to work with code. More specifically, work with code in order to develop your own active inference models. You've got to get, of course, enough of a handle on the code base in order to be able to think through your modeling, but that's the base. And of course, PYMDP is the gold standard. It's beautiful and it's also intimidating. And I personally am not going to go there for a while. Instead, through Themesis, we're developing a code base that is strictly pedagogic, meaning incrementing a little bit at a time, teaching you not only what the code is, but how to make those decisions. For example, how do you fill out a matrix of priors? All these things are important processes for you to undertake so that your experience of working with active inference is not just theoretical or conceptual or going through the equations, which I'll admit has been what I've been doing up until now, but becomes more hands-on. You will learn so much more in a very complementary way, and honestly, you'll have a lot of fun. So please check out our course. If you sign up as a learner, roosters, it's kawaii. If you go to the themesis.thinkific.com site and sign up as a learner, you can see what we make available for free in both the Top 10 Terms and the Building Active Inference in Python courses. Please check them out and definitely sign up, do the opt-in with Themesis, because we'll get you emails announcing when there's new materials. Often those materials are free for a limited time, so emails are the way to know. So on that note, it's been a lovely moment to share with you. Once again, Alianna Maren from Themesis. Thank you. Have a lovely day.